We're going to look at the second part of state space model for analyzing time series data. So in the previous video, we saw the core theory of how do we build a state space model, and more especially, how can we estimate the hidden states, how can we forecast in the future, and how can we smooth, meaning that how can we learn about previous state given future data, okay? So now we're going to put that into practice by seeing how can we build linear model structure that will be used to represent a vast array of possible physical phenomena and use them in order to build model for time series. Okay, just a quick recap. So the general formulation for state space model that we saw together is that we need two models. So first we need a transition model that will guide us into how does our state evolves over time. So our hidden states evolve over time. So the transition model takes this form where we have here the relation between the hidden state at time t-1 and the hidden states at time t. And this is obtained by xt equals a times xt-1, where a is a matrix containing deterministic coefficient, plus w, where w here is the error term. It's there to characterize the fact that the reality might not be exactly described by this linear model formulation. And here we assume that W is a realization from a Gaussian random variable, which has zero mean and covariance matrix Q, okay? Then we have also an observation model. So for our observation model, we say that YT, or actual observations, are equal to F, an observation matrix, times XT, where XTs are vector of hidden state variable at time t, plus VT. VT are observation errors, which are assumed to be a realization from a Gaussian random variable with, again, zero mean and covariance matrix R. In most cases, keep in mind, R is going to be a diagonal matrix. So here, if we just make a quick recap, A here in our transition model is going to be called our transition matrix. F is going to be our observation matrix. Note some references, and sometimes even myself, I use F or C for that observation matrix. So in this slide, I'm going to use F. In some codes such as BDLM, or sometimes even the books from the class, we're going to use it as C. And depending on the references, one or the other is used. So either you see F or C, it's the same thing. Q is going to be the mole error covariance, and R, the measurement error covariance, okay? So the key here is how can we build these matrices? So how do we choose A? How do we choose F? How do we choose Q? In order to represent, to describe specific dynamic we're trying to model, okay? This is what we're going to look at in this video. How can we build quick and easy generic subcomponents that can be adapted to a vast arrays of application and that can be used with state space model, okay? You can see that as building generic subcomponent, just like if it would be like Lego blocks, okay? So we could have different phenomena. One of the key phenomena that we keep using over and over is going to be the local level. The local level is there to model something that is locally constant over time, okay? Between two time steps, we assume it's going to be the same behavior plus some perturbation due to the fact that our model might not be an exact representation of reality. We could have something that is a regression block, okay? That's going to put in relation many time series. So the displacement of the structure might depend on the temperature, for instance, okay? So for that, we're going to need a regression block. We then have some periodic phenomena. For instance, we know really well that temperature oscillate according to something that looks like a sine wave, okay? We have periodic phenomena. How can we have some generic component that will represent such a periodic phenomenon? We could have short-term variation that are time-dependent, okay? We're going to model this with autoregressive component. We can have either zero speed, constant speed, or constant acceleration component to model some deterioration process or any accelerating or constant speed dynamics. And the beauty of this, of what we're going to see today, is that we can mix and match all these simple blocks, these simple subcomponents, in order to create really rich model that remain simple to handle mathematically and that are fully compatible with the state space formulation that we saw last week. Okay, so what we're going to look at today is how can we build these subcomponents, okay, that are generic and can be applied to a vast array of problems. Then we're going to see, okay, how do we handle then dependencies when we have many time series for which the subcomponents depend on each other? How can we handle that in the state space model formulation? And then we're going to look at, okay, what is the special case for the regime switching or the switching Kalman filter when we have multiple dynamics that come into play in order to model a phenomena? How can we do this with our same generic subcomponent? Then we're going to see, okay, once we know and we realize how can we define all these subcomponents, how can we use the existing packages, so in this case OpenBDLM, in order to make all that data processing automatically. So we're here in the second part of state space model for time series. Okay, so for subcomponent, first we're going to see multiple generic subcomponent that can be used to model or to create model for time series. Then we're going to see, okay, once we've identified and we've created the formulation for these individual building blocks, how can we assemble them together in order to create the complete model? Okay, and we're going to look at that through an apply example where we're monitoring the temperature recorded on a bridge. So the first block that is in almost every model is the local level. So the local level is there to represent the dynamic that is locally constant over time, meaning that I expect the behavior to be constant, except for the perturbation that could come from the process error. Okay, so in that case, if I want to use a local level block, I'm going to have a single hidden state. Okay, that single hidden state is going to have a subscript LL for local level. Okay, my A matrix, remember the transition model is xt plus 1 equal AXT plus WT. Okay, so my A is simply 1 here, is simply a constant. F is simply equal to 1. So my actual hidden state contribute to my observations Y. And Q, my covariance matrix, is simply a variance term. Okay, so if we want to look at how would such a locally constant behavior would look like, it would be like this. So if all my hidden states would start at 0, so if I generate many different realization of such a local level process, each line you can see here could be different realization. For the case where that variance parameter, for the standard deviation at least, it's equal to 1, okay? And depending on what is going to be the value of that standard deviation, it's going to affect the amplitude of the possible variability in my process. So if I make it lower, it's going to be a narrower band of describing all my possible process. So instead of I use 0.5, 0.25, it gets shorter, 0.1, and if I would use 0, they will all be perfectly constant. Okay, so here that parameter controls how much variability do I expect to observe over time. That's why we say locally constant, because if this is non-zero, it's not going to be perfectly constant. Okay, we accept that our model might not be an exact representation of the reality. Second block is for the dynamic that we know that will evolve at constant speed. Okay, so in that case, my vector of hidden state for local trend, oh, here a little mistake. It shouldn't be the red block, it should be the local trend block, okay, not the regression block. So if we have a local trend, in this case, I'm going to have two hidden states. So the level hidden state and the local trend hidden states, okay? So in that case, these two variables is going to represent a process that evolves at a local constant speed over time, or at the locally constant speed over time. We're going to look at this. So in this case, since I have two hidden states, my transition matrix has two variables. So it's going to be a 4x4. So in that case, I can say that XL at time t is equal 1 times XL at time t minus 1 plus delta t times XLT at times t minus 1. Okay, so it's the current coordinate plus the speed, so the rate of change, time the length of my time step. And for my local trend, so what controls the rate of change, it's simply 1 times my local trend time t minus 1. Okay, in that case, for the most common part for local trend, What contribute to my observation, as controlled here by my observation matrix, is 1 and 0. So it's going to be 1 times XL, because typically we don't observe the speed, we only observe the position over time, and we need to infer both the position and the speed. And here my covariance matrix, QLT, is equal to my standard deviation term, or my variance, times the coefficient here, that account for the fact that I can have an error in the terms that are omitted here. So here assume that I have a constant speed model. What if I have an error? For instance, I have an acceleration between two time steps. In that case, these terms that I have in that matrix are there to account for the fact that my process might not be an exact representation of the reality. So if we generate some realization for that error process, we can see that here on the horizontal axis we have time, vertical axis we have that level, on the vertical axis here we have the trend. Okay, so we represent over time different realization for both. So what you can see here is that for the trend looks exactly like the level was looking in the previous component. Okay, that's why we call it the local trend. So we assume that the speed is locally constant, and that is going to in turn affect how the level acts. Okay, so then this is defined by this parameter here. So the larger this parameter, the more change we're going to allow in the speed, the more fluctuation we're going to expect in the level. So it's if instead of being 0.1, it's 0.01, so much smaller. In this case, we're going to have a behavior which much less variability, both in the speed and in the level. If I take something even smaller, I can have an almost constant or constant speed behavior. Okay, so the locally constant or local trend means that here my speed is a locally constant quantity. Then we can extend the same thing to this time local acceleration. Okay, same principle. Now I'm going to assume that I have a model that has a locally constant acceleration. Then I'm going to have 3 hidden state variables, one for the level, one for the trend, one for the local acceleration. This is going to be my transition matrix, where, for instance, for the level at time t is equal to the level at time t minus 1 plus delta t times the trend, so the rate of change at time t minus 1, times delta t squared times the acceleration at time t minus 1. And we have the same thing here, a similar model for the speed, similar model for the acceleration. In that case, again, the classic formulation is going to assume that we don't only directly observe here the level here. Okay, we typically don't observe the trend, we don't observe the acceleration. If it would be different, you would simply modify that F matrix. So a little thing that I notice here, so in practice, you're going to see that the observation model matrix here should be a row vector. So there should be a transpose here on top of this column vector. In my Q, my process loss covariance is defined by this thing here, assuming that actually my model assumes that I have a constant acceleration over a time step. What if I have an error there? This matrix is there to account for the fact that over the time step, my acceleration might not be constant. And this is controlled by this parameter that controls the amplitude of that error I'm making. So at least of the stochastic process that controls that error. So in that case, as we said before, here we have on the horizontal axis time, vertical axis is in this case the level, the trend, so rate of change, and local acceleration. So we see that in this case, it's the acceleration that is locally constant over time. Okay, so we assume it's constant up to some time-dependent error that might make it evolve over time like this. So depending on the magnitude of that error, it can lead to large variation here, which will lead into large variation in the trend, large variation in the level. If I reduce this thing, it's going to reduce the uncertainty in both. If I put it to 0, these things will be completely constant. Okay, so if that goes to 0, the acceleration is going to be constant. The speed is going to evolve linearly, and the level is going to evolve quadratically. Okay. Now, another thing that is extremely useful to model natural phenomena is the periodic block. Okay, the periodic block need two hidden states. We're going to name them XS1 and XS2, where XS1 is the component or the hidden states that carry the amplitude of a sine wave. Okay, where in this case we have a parameter omega, where omega is equal to 2 pi times delta t, my time step length, divided by here p, the period of my periodic phenomena. And that omega is my frequency for my periodic signal, okay? So from that frequency, I can build my transition matrix. So my transition matrix A superscript S for my periodic component is going to be cos of omega, sin of omega, minus sin of omega, and cos of omega. So this is what we call the periodic component expressed in its Fourier form. So in this case, again, this should be transposed. We only observe the amplitude of the signal, okay? So my second hidden state variable is not directly observed. It's only there to make the transition between time steps using that transition matrix. My covariance here is equal, we can assume that we have uncertainty only on the diagonal. So these two components are independent, such as here, my variability is going to be controlled by, again, this variable, my standard deviation for my periodic component. So in this case, we can have different realization, either for my first hidden states or my second hidden state, okay? Here, my period is 10. So you can see on the horizontal axis, we have time. So if the period is 10, we are going to make one cycle over 10 time step, okay? So in this case, this is here my noise parameter here. So the smaller is going to be this, the closer is going to be to a perfect sine. The larger it is, the more variability I can have in both hidden states. So instead of using 0.01, I use 0.1. We see that we greatly increase the possible variability in my hidden states. If I instead of using something much smaller, it's going to tend to a perfect sine wave. If instead of using a period of 10, I'm going to use a period of 20, then I'm going to make one cycle over 20 time steps, okay? Then we have the autoregressive time series, so or autoregressive component. In that case, we use this because when we build these linear models are always going to be imperfect representation of the reality, okay? So we need a component that's going to take into account the fact that we have an imperfect representative reality with our linear model. In this case, since we are trying to model time-dependent quantity because we're looking at time series, our errors that we do with our linear model are also not going to be time-dependent, meaning that if I'm having a given error at time t, I'm likely to have a very similar error at time t plus 1. So in here, typically the autoregressive component is there to capture those time-dependent errors, okay? For the special case of where we say an autoregressive process of order 1, we're gonna have only one hidden state, okay? XAR for autoregressive. My transition matrix is here phi AR, it's gonna be my autoregressive coefficient. I'm gonna directly observe this this hidden states when I'm gonna have the observation model. So my observation is gonna be depending on this hidden state variable, and I have in my covariance matrix only my variance parameter for the autoregressive component. And here, that autoregressive variable must satisfy some properties, okay? If we want that AR process, so autoregressive process, to be stationary, meaning that it's going to have constant parameters, so constant expected value and constant variance over time, for it to be stationary, we need to restrict that autoregressive coefficient to be between 0 and 1, okay? So in that case, it will lead to a parameter that is stationary, meaning it has the same expected value, no matter where you are in time, the same standard deviation. And the stationary standard deviation it would lead to is defined by here that autoregressive variance that you have here divided by 1 minus that autoregressive coefficient square, okay? That's going to be what describes the stationary variance of my autoregressive process, So what you see here is examples again of realization where all the value starts at 0 and we generate different realization. So under horizontal axis, what we have is time, vertical axis is the AR process. So what you see in the pink region is the expected value, which is going to be 0, plus and minus that standard deviation, so the square root of what we have here. So we see that this is the standard deviation describing the stationary standard deviation of my autoregressive process. And here the phi AR, so the autoregressive coefficient is 0.8. The standard deviation is 1, okay? So what happens if I use a smaller standard deviation? So you see that we have less variability in our model, okay? And here what you see is that the process is time dependent. So I can go from large value to smaller value, but my process is dependent over time. So the current value depends on the previous one by this autoregressive coefficient, okay? So larger standard deviation here leads to broader or more dispersed value, smaller to smaller, less dispersed value, and it also modifies the stationary standard deviation. What if you use even smaller value? What if we compare here by using some different autoregressive coefficient? So we see by using smaller value of autoregressive coefficient, compare here to there, we see that we have more variability here. So at least more short-term variability compared to here, okay? So here we have, with a phi AR of 0.8, we have more long-term fluctuation. With phi R equal 0.2, we have more short-term fluctuation, okay? So this is a more independent process. Then if we do the opposite, we use phi AR values that are much closer to 1. In that case, we're going to have much longer term variability, okay? And if we use something that's above 1, the process is, if we have or above or equal to 1 for phi AR, in this case it's 1.1, the process, if we generate minimum realization, it diverges, okay? It won't lead to a stationary standard deviation. So it means that the standard deviation is not constant over time, okay? It keeps growing, for instance, in this case. And in the special case where phi AR is equal to 1, in that case, the process is the AR process is exactly equal to the local level we had before, because you can see here, if we replace this by 1, this is exactly the same formulation as a local level. So now if we're assembling subcomponents, because we're going to define all these specific subcomponents, then what we're going to do is that we're going to need to assemble them together in order to create a single model. So for instance, what if I want to assemble together a local level, a periodic, and an autoregressive component? In that case, what I'm going to do, I'm going to take the respective hidden states for each component, and I'm going to concatenate them in a single larger vector. So I have here my single hidden state for local level, my two hidden states for the periodic component, and my single hidden state for the autoregressive component. Here, the order of the hidden state variable or the component is not important, as long as you're consistent with building your matrix and reorganizing your matrix A, C, Q, R, etc. Then for the observation and transition model matrices, A and F. So in that case, what you're going to do is that you're going to do the same thing. You're going to concatenate on the diagonal of matrices all the F matrix, the A matrix, the Q matrix, and the R matrices, okay? So for instance, you're gonna have an F matrix for the local level component, you're gonna have an F matrix for the periodic component, and an F matrix for the autoregressive component. So what you're gonna do is build a larger matrix where on each diagonal, where you're gonna have those matrices. So a little reminder that what we say in the linear algebra part is that if we have two matrices, A and B, and we want to build a block diagonal matrix from A and B. What it means is that I'm going to build a larger matrix that's going to the size are going to be the sum of the dimensions. So it's going to be, in this case, a 5 by 5, where I'm going to concatenate on the main diagonal my two matrices, and it's going to be 0 everywhere else. Okay, so this is exactly what we're doing here. Okay. So here we're going to look at some data, okay, some data set. What we have is some temperature data. So we have here from 08-2013 till 10, so October 2015, okay? So what you see here is temperature data recorded on a structure, okay? The horizontal axis is time, vertical axis is the actual temperature, okay? So this, in practice, for my algorithm, is going to be a vector of observation from y1 up to yt. So what we want to do here is to use some of the generic subcomponents we've seen together in order to build the model for that time series. So in that case, we're going to say, okay, first I'm going to use a locally constant component, okay, to represent what is the average temperature of my data set. Then I'm going to use a first periodic component to represent the yearly cycle in my pattern, okay? And here, keep in mind, a year doesn't have a length of 365 days. The real periodicity of a year, so the time it takes for the Earth to circle the sun, is 365.24 days, okay? That's why every 4 years we have an extra day. That in those bissextile years, it's to account for the fact that our calendar length is 365 days, whereas the real length is 365.24. But if you want to model the real phenomena, you cannot use a calendar year. You have to use the real solar year length. So the period here is 365.24 days. Then on top of this, we don't clearly see it because we have too many data points here, but we also have a daily pattern that is overimposed into it. So we need a second periodic component with this time a period of 1 day. And we want to add an autoregressive component to try to capture what is not captured by these other hidden state, but which is not observation errors, okay? So to do this, we're going to use the block we've seen. So first block, a local level, 2 periodic component, and an autoregressive component, okay? So what we're going to do, as we discussed before, we're going to build ourselves a larger concatenated vector, which contains all of our hidden states, okay? So local level, the 2 hidden states for my first periodic component, my 2 hidden states for my second periodic component, and my autoregressive term here. Then for my A matrix, my transition model, I'm gonna build a block diagonal matrix with all the respective matrices for each component. So here I have my local level, first periodic component, second periodic component, and autoregressive coefficient. I'm going to do the same for my process noise or my process error. I'm going to build my block diagonal matrix, my F matrix. So my F here is going to contain or is going to indicate with the 0 and 1 which hidden state is observed, which one is not. So in this case, 1, 1 indicated the 2 first hidden states are going to contribute to my observation Y. So the local level contributes, the amplitude of my first periodic contributes, the third one is 0, so this one won't contribute to my observation. The fourth one will, the amplitude of my second periodic component, the fifth one won't. And the last one, my autoregressive, does contribute, okay? So my F matrix here is there to indicate which hidden states contribute to my observation, which one are not. Then R is going to be my observation errors. So my observation errors, the covariance for my observation errors. In this case, I have only one time series. So my covariance matrix is going to be a 1 by 1. It's going to be simply the variance for my error process. So at the end, here in this generic vector, many components can be assumed to be stationary. So whenever they're assumed to be stationary, we simply set their variance to 0. So in this case, the only one that I'm assuming that I have unknown parameters that are going to be non-stationary, or at least that I have unknown parameter, is going to be the autoregressive process, which always have an unknown standard deviation. We have the autoregressive coefficient that is unknown as well, needs to be learned from data. And I might not know what is the standard deviation for my observation errors, okay? So I have only 3 parameters that I will need to learn with, for instance, MLE maximization. Okay, so in order to analyze my data, I'll need to define initial expected vector and initial covariance for my prime knowledge at time t equals 0. Okay, so here if I have 1, 2, 3, 4, 5, 6 hidden state, I'm going to have an expected vector with 6 value, a covariance matrix 6 by 6. So in that case, I'm going to assume that my expected value for the temperature is 6 degrees Celsius. The other ones, I have no clue where to initialize them. I'm going to initialize them at 0. I'm going to have a moderately large standard deviation for my first one and a much larger one for the other ones, just because I don't know at what value to initialize them. So this is the prior expected vector, prior covariance for my hidden state vector. So now that I have defined all my model matrices, so A, F, Q, and R, I can use this in the Kalman filter, okay? So I can recursively do the update step in order to obtain my posterior expected value, posterior covariance for each of my time steps. And here, remember, I have 3 parameters to infer. I need to infer the observation error standard deviation. I need to infer the autoregressive process standard deviation and the autoregressive coefficient for my AR process. So these 3 parameters need to be optimized by looking which argument theta from these 3 parameters is going to maximize the sum of the log likelihood for all the time step in my time series. Okay, so if we do that process, obtain our optimal parameters, and we do the smoother for estimating my hidden state, it would look like this. So we have the time from 2013 till 2015. This is my local level. This represents my average temperature over time, which is here about 6.3 degrees Celsius. We have a periodic component. So here in that case, we have extracted the yearly periodic pattern from my data. And we have on top of this a daily periodic pattern. So here it looks all black. Why? Because I have so many fluctuations. I have so many daily cycles that I cannot even see them. But here it's because over the scale of 3 years, I have a sine wave with a period of 1 day that is oscillating all the time. So it looks just like a big black blob. But it's many, many sine cycles. And finally, I have my autoregressive process here that represents my errors, okay? It represents what was not correctly modeled by either my local level, my seasonal periodic component, my daily periodic component, and that is neither observation errors, okay? So this is kind of my trash term. What is there? What is not correctly modeled by my linear model formulation, but is not observation error, okay? So if you want to see the details of how to build these basic blocks, how to assemble them together, and how to apply them to time series, you can go see those 2 references. And keep in mind, the block I've shown you here are the basic building block, the simplest one. But you can see already they have many, many more advanced model formulations for creating much richer model that can adapt to a vast array of situations. If you want to see the most up-to-date component, you can go see on the website from my research group. We have many papers where we showed all these components. The more advanced ones that can go beyond what I've presented here. Okay, so in the second part, what we're going to look at is how can we model dependencies. Okay, how can we model dependencies between several time series? For instance, what if we're trying to monitor over time the behavior of a structure? And we know that that behavior is influenced by the external temperature or maybe the traffic load. Okay, in that case, we want to create dependencies between the hidden state of each of those time series. We're going to see how can we build our state space model with those linear dependency built into them. Okay, so we're going to look in more detail a bit at the context of these dependencies between time series. Then we're going to look how can we adapt a specific component to take care of that dependency. How do we assemble the subcomponent in the case where we have dependency between time series? And we're going to put that into practice where we want to explain the displacement of a structure over time as a function of the observed temperature on that structure. Okay, so here's the example. These are 2 real time series. The top time series is going to be the displacement of a structure over time, okay, from 2013 till 2015. The second temperature, or the second time series, is going to be the temperature recorded from 2013 till 2015. So here we have two time series, where first one has a superscript D for displacement, the second one has superscript T for temperature. And one first thing we can see is that there's clearly dependency between these two time series. Here we can see that there's, for instance, a negative correlation for the seasonal pattern. For instance, we can see this because we see that when the temperature, or when the displacement is large, coincide with the time where the temperature is low. In the opposite, when displacement is low, it corresponds to the case where temperature is high. Okay, so that represents the case of a negative correlation, or a negative dependency, or a negative regression coefficient between my two time series. Okay, and to do this, we need to introduce a new block. So here I have a problem. This is not the local acceleration block. It should be the regression block. So a little typo here with the block name. So local acceleration is the regression one. So the regression block won't have variable on its own. Okay, so no state variable on its own. Instead, this block, how it's going to do is going to introduce in a global observation matrix for several time series some regression coefficients. Okay, so Fij represent an observation matrix which represent the dependency between time series I and time series J. Okay, so in this case, we're gonna put in that matrix some regression coefficient phi, which are defined in the real domain. So it could be from -infinity to +infinity, and then going to take care about to express the linear dependency between the hidden state for one time series and the hidden state for the other time series. Okay, or more, the observation for the other time series. Where here that the regression coefficient is defined in the real space, and it should be interpreted as a regression coefficient. So when we have multiple time series that we want to analyze together, okay, what we're going to see is that we're going to build global observation matrix, transition matrix, error covariance, so model error covariance or observation error covariance. Okay, we're going to build these model global matrix from the local one created from each time series, as we've seen before. Okay, so in this case, we have only two time series, displacement and temperature. So we're going to build global matrices by concatenating in block diagonal matrix the F matrix for the displacement, F matrix for temperature. Same thing for A, Q, and R. Okay, so we're going to look in detail how it works. But before, let's look at how do we define that F matrix, where we're going to have our regression coefficient. So here we're going to say F, our observation matrix, is going to be our global observation matrix. So what we have on the diagonal of this F matrix are the local observation vector or observation matrix for each of my particular time series. Then on the off-diagonal terms, what I'm going to have is the specific regression coefficient that will represent the dependencies between the hidden state for one time series and the observation for the other. And in that case, we're going to encode a matrix, a new matrix, which is D, where D is the dependence matrix. So we're going to say the diagonal is always 1. In the diagonal, off-diagonal terms are taking values either 0 or 1. So if it's 0, meaning we have no dependency. If it's 1, we're going to have dependencies between the two time series. Okay? So if Dij here for the off-diagonal term is 0, Fijc, which you can see are the off-diagonal term here, are equal, it's a vector of 0. So it represents no dependency for the time series. So the result we're going to obtain is the same as if we would analyze the two time series separately. However, if Dij is equal to 1, it means we really want to create dependency here. So it means that my observation matrix for my off-diagonal terms Ij is going to be a vector of regression coefficient, each defined in the real space. Okay, so phi ijk represent the linear dependence between the kth subcomponent from the jth time series and the observed response for the ith time series, okay? So in that case, if we put that into application, we have again the top time series here is the temperature observed. The bottom one is going to be the displacement, okay? And as we said before, we have negative correlation between the two because when temperature is high, displacement is low, okay? We have the temperature is the same temperature we detailed before, and we said we defined explicitly what were our 6 hidden state for the local level component, first periodic component, second periodic component, and autoregressive component. Then what do we do with displacement? So with displacement, we see that we still have some periodic phenomena, okay? But what we want to avoid doing is doubling the periodic component. Why? Because actually these two depends on each other. So we want the displacement here for my structure to depend up to a regression coefficient on the hidden state I've already defined here. So at the end, for my displacement time series, I'm going to have only 2 hidden states, okay? A local level and an autoregressive coefficient. So now I will build my global vector by concatenating the vector for the displacement and the temperature. And then I'm going to concatenate in the same way all my hidden states in a single vector, where my first 2 are going to be my hidden states related to the displacement. My 6 last are going to be the hidden states related to the temperature, okay? So now let's look at just the model matrices for the temperature. We're going to have our A model for the temperature. This is the same as we defined before, Q, F, and R, okay? This is exactly the same model structure as we explored together in the previous subsection. Now, we said that we have 3 parameters, the same 3 parameters as before here. Now, let's look at the displacement. So we have 2 hidden states. So my transition matrix is 1 and phi AR. So 1 for the local level, phi AR for the autoregressive component, Q, F, and R, okay? Now, my 3 unknown parameters are going to be my standard deviation for the autoregressive process for the displacement, my autoregressive coefficient for my AR process for the displacement, and the standard deviation for the observation noise for my displacement. Okay, so now if I want to assemble together my 2 hidden state vector, okay, I'm going to build global block diagonal matrix for my 2 time series. For here, displacement, temperature for A, F, R, and Q. And note here we have something specific for my observation matrix because this is where my regression coefficient are going to appear. So if I assume that my observation matrix is diagonal, in that case, it would lead to a F matrix that looks like this, okay? I have my first F matrix for my displacement in blue, and I have my second observation matrix for my temperature in red, okay? And since this term is 0, I have 0 in that term here. What does it mean? It means that my displacement is independent from my temperature. So whether in that specific case, whether I would independently process my 2 time series or process them together would lead exactly to the same result, okay? But this is not what we want to do here. We want to have some dependencies between the hidden states for my temperature and the displacement response. So in that case, I want to introduce a 1 here in order to generate some regression coefficient. And here I want non-zero regression coefficient for this one, the 4th hidden state, 1, 2, 3, 4, meaning the amplitude of my seasonal pattern in the temperature, 5, 6th. My 6th one is going to be the amplitude for the daily periodic pattern for my temperature, and I want another regression coefficient for the last hidden state, which is going to be my autoregressive variable, okay? So in that case, I've grouped these autoregression or these regression coefficients into 2 groups. The first one and these 2 ones are the same one, the second one. Why? It's because here what you have to see is that both the daily pattern and the autoregressive pattern are going to model short-term effects, okay, from the order of the hours up to the days. Whereas my seasonal periodic pattern here represent effects that occur on the course of months, many months, okay? So these two have two different time scale, and we're gonna see that this is gonna lead to different regression coefficient for a long-term effect and short-term effect. And how do we do this? We need to optimize these parameters. So my global vector of parameters that I need to optimize include the 6 parameters I've defined before. So the autoregressive coefficient, the standard deviation for the autoregressive process, and the standard deviation for the observation errors, okay? So autoregressive coefficient, standard deviation for the autoregressive process, and standard deviation for the observation errors. The last 2 parameters that I need to infer are these 2 regression coefficients. So sigma dt1, sigma dt2, okay? So in that case, I use an MLE approach based on the Newton-Raphson algorithm in order to optimize these optimal parameter values. And in that case, let's look at the specific value we obtain for our regression coefficient. So in that case, the long-term effect here controlled by phi d given t1 is minus 0.02, and the short-term effect is plus 0.01. What does it mean? It means here that long-term effects represented by this coefficient are negative. And this is what we observed before. So before we said that the long-term effects are negatively correlated, meaning that when the displacement is low, temperature is high, and vice versa. And this is what we obtain here in the sign of the regression coefficient that were inferred by the optimization algorithm. We have a negative coefficient that corresponds to the dynamics we've observed visually in the data. But for the short term, we see a positive value. What does it mean? It means that the short-term effects, so the daily variation in the temperature, as well as the autoregression, which also represent daily variation, are positively correlated. Okay, so here it shows how important it is to separate into subcomponent the time series if we want to model dependency, because some subcomponents are going to be positively correlated, some other are going to be negatively correlated. If you would have wanted to do simple linear regression between the 2 time series, it would have simply not worked, because you have confounding effects such as the short-term effects are positively correlated, the long-term effects are negatively correlated. So if you want to make that dependency, you have to divide your time series into its subcomponent as we have done here. Okay, so before processing the data to estimate the hidden states, we need to define what is going to be our initial expected value in covariance. So in that case, we define the expected value of 26 for the displacement, so 26 millimeters. 6 degrees Celsius for the temperature, and the other ones we initialize at 0. And we initialize the variance to some values that are fairly large given our prior knowledge for this problem. Okay, so now we've defined all of our global matrix A, F, Q, and R to jointly estimate both time series. Okay, and again, we do that here using either the Kalman filter or in this case, this Kalman smoother. So you can see here for the local level, this is the average or the long-term constant displacement of the structure, which is something close to 26 here millimeters. We can have here the autoregressive component for the displacement. And then we have all the hidden states associated with the temperature. So here, why don't we have any periodic phenomena for the displacement? It's because this one is all explained by the long-term seasonal effect from the temperature or the short-term seasonal effect from either the daily periodic component or the autoregressive component from the temperature. So we can put in relation several time series in order to jointly analyze them. Okay, so now we're going to look at what happens if we want to build model in the case where we have regime switches. So change in dynamic that explain our behavior. So we're going to look at this through the data recorded on a dam. So what you see here is a model for a dam. This is upstream, this is downstream, this is my dam here. This is east-west. And what we're going to look as in terms of time series, we're going to look at an inverted pendulum. So inverted pendulum is there to model or to measure the displacement of a dam over time. So the basic principle is that we have a wire here that is anchored into the bedrock. And on top, what we have is a floating device that floats into a kind of large pool of oil, meaning that this vertical force by the floating device is going to maintain the verticality of the wire that attached this floating ball onto the bedrock. Okay, so then by looking at using this table, the relative position of the table, which is bolted on the structure, and the cable, we can look at the movement of the structure with respect to that vertical reference point. Okay, so this is called inverted pendulum. Then let's look at this data set. Okay, this is data recorded on that structure that ranged from 2002 till 2016. So you can clearly see we have a periodic pattern and we have a downward trend. Okay, so in that case, what we want to see is we want to try to detect anomalies in real time on that time series. So we're going to build two model structure. The first one for the normal behavior, which is going to be a constant speed model. So that in that case, we're going to have a local acceleration component for which we're going to put all the acceleration component. We're going to force them to be 0. Then we're going to have a periodic component and an autoregressive component. Then for the abnormal model, we're going to have that autoregressive, that locally acceleration component. But in that case, we're not going to set that local acceleration component to 0. Okay, we're going to let it free to be whatever it needs to be. And we're going to put these two in competition with each other using the switching Kalman filter, for which we described the theory in the previous part 7a. So, okay, for the hidden state variable, so in both cases, as we said for the SKF, both model structures must share the same hidden states. So in that case, since we have in both cases a local acceleration, so it's going to be a level, a trend, and a local acceleration component. Then we're going to have two periodic phenomena. In that case, why do we have two periodic phenomena? It's because, as you can see on the raw data, this is not a fully periodic pattern. Okay, there's a little flat part in the middle of summer. There's a little like pointy part in the winter. So in that case, in order to model this, we can do it by the superposition of several harmonic signals. So in this case, my first one is going to have a period of 365.24 day. The second one, half the period. And the superposition of these two is going to make something that looks like a square wave on top. Okay. And the last one is going to be my autoregressive hidden state. For my model, the only specificities that we haven't covered before is now, okay, I need two different model matrices, notably for my local acceleration. Why? Because my first model, we say that we're going to set the hidden state associated with the acceleration to 0. We do this by putting my third column to 0. What it means is that the local acceleration is always going to be there, but it's going to be forced to be 0 at any time step. For my second model, which represents the abnormal model, it's going to have the full model matrix for my local acceleration term. Okay, so here the two model I'm going to put in competition is one with a constant speed, the other one with a non-constant speed. Okay, so constant speed versus constant acceleration. And then I need to define a model transition matrix, okay, the probability of switching between one regime and the other. And I'm going to parameterize this between Z1 and 1, the probability that if I'm in state 1, I'm staying in state 1. This is its complement. The probability that if I'm in state 2, I'm remaining in state 2, and this is its complement. Okay, these are two parameters that need to be learned using, for instance, an MLE approach. Okay, so now if I want to use this, I'm going to look at this here. So what we have here is the data. So we say that we're going to use 5 years of data as our training period to learn all the parameters in our system. Okay, Then we're going to simply collect data over time, and the system is going to return what we have on the bottom, the probability of each regime. Okay, in this case, it's the probability of the regime 2, the abnormal one. Okay, the one which allow acceleration. In that case, for the first 5 years, we see that the probability of having acceleration is close to 0. Okay, I'm going to start here the animation, and I want you to tell me, when do you think we have the anomaly coming in? Okay, so this is the Kalman filter analyzing data in real time as data comes in. Okay, so the probability for the abnormal regime is still very close to 1. You see that now we have a trigger. You see that here it detects, as the data was received, that there was something going on here. And then it switched back to say the probability of my abnormal model goes back to 0, and I have a 0 speed model again. Okay, this is how it can detect in real time anomalies, so change between a normal and an abnormal regime as data is collected. Okay, so what we can see here, we see as a function of time, vertical axis in this case is the raw data, in this case is the baseline. You can see a jump here. Okay, on that jump, what we can see is that something happened on the structure, and using our hidden state, notably the rate of change of the structure, we can look in this case at the rate of change before and after intervention. So before intervention, the rate of change was 2 millimeter per year. After intervention, minus 2.9 millimeter per year. Okay, so if we look in more detail, this is the raw data. This is the probability of the abnormal regime. So initially it was 0, they didn't jump, and the green one's going to be the complement, so the probability of the normal regime. So remember here, normal is constant speed and abnormal is constant acceleration. Okay, and here we know actually that something happened. We know that actually the owner of the structure made some reflection work on the dam. Okay, but using this time series analysis, we can quantify as data come in what was the rate of change before and after the intervention. Same thing for acceleration. We have here the periodic pattern, the hidden states for the 1 year component, for the 6 months component, and here we have the autoregressive component, which represent the model errors associated with everything that is not modeled by our current model formulation, but that is not observation errors. Okay, if you want more details about how does this thing work, you can look at all the details that are represented in this references, Nguyen and Goulet, anomaly detection for the switching with a switching Kalman filter for structural health monitoring. So all the details are in here and all the interpretation of the results. So now, okay, we've seen how all the model formulation works. Now, how can you automate all this, and how can you rely on existing pieces of code in order to analyze time series? Okay, and you can do all this using the OpenBDLM package. So how to get started with that package? How can we use configuration files in order to configure, to build your analysis, to build your model? And then we're going to look at some example of applications, okay, some practical example. So OpenBDLM is available on GitHub. You can go and download that package. It's in MATLAB. So the way you use it is that you download the folder openbdlm.zip, you unzip it, you put it somewhere on your computer, and you go in MATLAB and do add with subfolder for everything that is in that directory. Then you set your working directory to OpenBDLM, the main folder where all the subfolder are. Then the main file that's going to control the flow of the problem is openbdlm __ main. And when you're going to work, as we're going to see next, you work with config files. And these config files should be put in the folder, which is in the subdirectory config files. When you want to have some data sets, the OpenBDLM expect all your data sets to be in the folder, the subfolder data. Okay, so you have to make sure that you respect that nomenclature. So how do we use OpenBDLM? So we have 3 different modes. The first mode is the interactive mode. You don't want to work with a config file. You just want to interactively build all and go through all the steps by being guided by the OpenBDLM itself. So to do this, you directly call OpenBDLM main. And you have some optional outputs, which are going to be the data. So it's going to save the data itself, the model, all the specificities associated with the model you will have built, all the estimations for your hidden states, and some MISC variable that defines the specific analysis you are doing in the instances where you use OpenBDLM. So this is good, but this is really long to use because you have to manually enter everything you want to do. So if you want to automate and accelerate the processing, you can work with config files, okay? Because at the end, you're going to see all the models are very similar to each other. So what you can do is directly build a config file and either use it for your own purpose or share it with someone else if you're doing analysis or if you're working with someone. Okay, in that case, that config file is going to be read and the model is going to be automatically loaded into OpenBDLM. And finally, the third feature is if we want to do batch mode. In batch mode, not only we want to load the model, we want to do operations such as estimating hidden states, producing plot, and everything. So not only it takes as input a configuration file, but also some actions to be done, okay? So all the details regarding this, go see on GitHub. We have full documentation of how every feature is working in the written documentation as well as on the YouTube channel. So first thing, we're going to look in more detail in how does the config file works, because this is the most convenient way to use OpenBDLM. So for instance, imagine we want to analyze this displacement data over time. Okay, so we're going to define 4 components: a local level, 2 periodic component, and an autoregressive component. Okay, how would we call OpenBDLM for this? We're going to give our 4 output variable and OpenBDLM main with a config file. Okay, and what would that config file look like? Somehow like this. Okay, we need to define a project name. Okay, then the project name is going to be called this. Okay, but you call it whatever you want. Then we need to tell in the config file where's the data for that specific problem. Okay, the data is in a matrix called data underscore this. Okay, .map. Where in that structure, what we're going to have is that.value contains the value. So we need to say data.value. So this is that structure, data.value, that OpenBDLM is going to use to say these are my Ys, okay, my actual observations. It also needs what are the timestamps, okay? At what time did I observe those Y? So you need to store your timestamp in that, that.timestamps. And finally, for the plot, you might need to put labels on your axis. So what are the vertical axis? In this case, we're going to call it this, okay? But you can call it whatever you want. So then we need to define what are those 4 blocks. Okay, you don't want to manually have to enter all your blocks. This is already all built in OpenBDLM. The only thing you need to do is to say, okay, my first block is going to be 11, second one 31, 31, and 41. Okay, so automatically it's going to create all the maths necessary to define your 4 components. And you're going to see appear all the possible parameters you have for these 4 blocks. And some of these parameters are going to be, for instance, the period, where in this case, for the first block, you're going to define a period of 1 year. The second period, for instance, 1 day. Then we're going to have the inter-component dependency. So in this case, since I have only one time series, or I'm going to have only one time series, so there's not inter-component dependency because I have one time series, so this is empty. So one thing we need to look in a little more details, what are these timestamps? Okay, there's specific way to deal with timestamps because we need a referential, okay? If you type now in MATLAB, it's gonna return something like this, okay? Where this numbers represent the number of days since 0101 year 00, okay? So this is a number in days since the year 0. So if you do date string of now being this thing, it will say, when I type this, it was March 21st, 2018 at 9:49:11 in the morning, okay? So you need to use that nomenclature for your timestamps, okay? In order for BDLM to, you and BDLM to have the same time frame. So basically an increment of 1 in the timestamp represent an increment of 1 day. Okay, so what if we want to use BDLM to model a dependency between several time series? So we look at together earlier the example, we have displacement, which depends on temperature, okay? And we see that here we had 4 blocks for the temperature, so local level, 2 periodic component, daily and seasonal, and autoregressive. Whereas we had only 2 blocks for the displacement, local level, and autoregressive, because these 2 blocks, the dashed one, are actually dependency over either the long-term or the short-term effects. So in that case, we again call OpenBDLM with a new config file that's going to look like this. So part A and B looks exactly the same, except that now in data.value, I'm going to have a vector which is going to have 2 columns. First column is going to be my displacement. Second column is going to be my temperature values. Okay? Timestamps, I must have the same vector of timestamps for both time series. Okay? And I have now 2 labels. The first label is for my first data set, in this case displacement, second data set temperature. Okay? Now I need to define in those brackets 2 vectors. Okay? Which block are associated with each component. So block 11 is local level, second block is 41 autoregressive. My second vector is for my second blocks, second set of blocks. So 11 local level, 231, so 2 periodic, and 41 an autoregressive block. And finally, we have to say, okay, what depend on what here? So we see that we have 2 placeholders, one for the first vector, a second one for the second vector. So in this case, we say that the first vector depends on the vector number 2, the second one. The second one depends on nothing, so no dependency. So that's going to automatically create the regression coefficient in my observation matrix F, and is going to treat this as unknown parameters to be inferred from data. What if we have a regime switching problem? Like here we have constant speed, zero speed regime and constant speed regime here. So I'm going to build a first model which consists only, for instance, of a local level, second one only of a local trend. Okay, I built myself a config file that will look like this. So the first 2 parts are exactly the same as before, but now I don't have a single model component, I have 2 model components. Okay, so the second model component is a local trend. So local trend, the code number for it is 12. And my first one, my local level, is 21. So notice before, my local level had the code 11. 11 is for a local level with 1 hidden state variable. In this case, it's 21. 21 is for a local level compatible with a trend, meaning it's going to be a local level or a local trend for which the trend variable was set to 0. And in this case, I don't have intercomponent dependency. We leave this one empty. Okay? So here are some examples of application of usage of OpenBDLM. So what we see here is the raw data. What we have is the water flow that runs through a dam. Okay, this is a key part for the engineers in order to know, is my dam healthy? Okay, the less water flowing through it, the less cracks I have, the better its condition. Okay, so this is a key thing to monitor for a proxy of the dam health. See, on the horizontal axis, we have data from 06 till 2014. Vertical axis, we have the flow rate in liter per second. So all of this is data, and we use, in this case, data up to 2013 to train the model. And then what we want to do is not use the data in blue here, just to make the model forecast, just to compare our capacity to forecast with OpenBDLM. And as you can see here, the dashed line is the expected value. The shaded region is the plus and minus 1 standard deviation confidence region. And you can see that we can be really good at forecasting the data we have not seen yet, okay? But this forecast is actually the superposition of everything else. So superposition for the local level, you see that there's an upward trend. That upward trend is characterized by this rate of change that is calculated by the local trend. We can see we have a periodic pattern. This periodic pattern is not the Fourier form we've seen. This is one based on kernel regression. If you want more detail, go see on our research group website. You're going to see how does this work. It's directly built in OpenBDLM. So there it's there to model non-harmonic periodic component. And in this case, not only it's non-harmonic, it has a non-constant amplitude over time. So you said the amplitude grows over time. We can directly build that in OpenBDLM. And we have our residual term here expressed by the autoregressive pattern. So the sum of those four hidden states make the signal you can see here. So that was for a first time series. We can have the anomaly detection. So the regime switching that we've seen before. This is the case of the dam here. We have the switch in the probability for the abnormal to the abnormal regime, which is a proxy for the probability of anomaly in my behavior. We can see here the smoothed behavior obtained. This is forecast. We have here in the local trend, the rate of change in my behavior. So we see that we have a higher speed before than after the anomaly, which was caused here by an intervention on the structure. We have the kernel regression. So with the kernel regression that represents the pattern, you see that here the kind of periodic pattern is more squared when we have high value than we have low value. We capture that adequately here with the kernel regression pattern. And again, the autoregressive part, the part that is not explained by an order component, but is not observation noise, is described here. Okay, then another application. Imagine that we're looking here at the data. So vertical axis is the temperature recorded at Montreal Trudeau International Airport. On the horizontal axis is time from 1953 till 2013. So we want to look at here, is there any effect of climate change? Is there any variation in the long-term effect of climate? It's really hard to see. But if we decompose that raw time series into its subcomponent, we can clearly see what's going on. So in that case, we can look at the local level with respect to time. You can see that here, if we remove all the yearly periodic effect, we can have a decreasing behavior from the 50s till to the 70s, and from the 70s on, we see an increasing temperature. And we can quantify that decrease or increase in temperature, at least its rate of change, by looking at the local trend value. So here, since one time step, the length is 1 day, the units, for instance, for the rate of change are going to be degrees Celsius per day. So if I want to have degrees Celsius per year, I'm going to take the value here. For instance, in 2013, the rate of change was roughly 0.17 power 10 to the minus 4 degrees Celsius per day. If I multiply this by 365, it's going to give me roughly 0.06 degrees Celsius per year. So it means the rate of change now is over 1 degree Celsius per 20 years. But keep in mind, you're still in high uncertainty represented by the standard deviation here. In that case, it's 0.05 degrees Celsius per year. So it can be either much greater or smaller than the value we can have here. So the value is strongly positive, but we still have a lot of uncertainty about this exact rate of change. You can see here the yearly periodic pattern. You can see the autoregressive part of this model here. So in conclusion, everything we've seen together for a state-space model is directly built in OpenBDLM. All the code is freely available on GitHub. You can download it. You have all the documentation to use it. Many applied examples, so many tutorial examples are available, and also many video tutorials that are available on the YouTube channel. So if you type OpenBDLM, you're going to find a channel, many hands-on example on either how to get started, how to handle configuration files, and how to load and do all the steps to process your data. Okay, so if you want to know how to use it, either go look at the paper documentation or the video documentation associated with OpenBDLM. So what is available for you? Pre-processing tool in order to load the data, to synchronize the time step in the case where you're going to have multiple time series, to resample the data, to, for instance, aggregating daily data to weekly data, the weekly data to monthly data, etc. You can process data with three modes, either interactive, where you're going to have queries from OpenBDLM and you directly interact to create config files. You directly build your own config files and load them into OpenBDLM, or in a case where you have multiple time series, you can work in batch mode to automate the data processing step. So it's an automated procedure. So it's going to automatically build the model. It's going to automatically construct the model by what you define in your config file. So you define the blocks, and automatically it builds the mathematical formulation for you. There are many either MLE approach or Bayesian approach to estimate the model parameters. So all the parameters that you can have in your model can be either estimated using MLE approach or a Bayesian approach, either using the Laplace approximation or using sampling. And otherwise, we have several optimization algorithms such as Newton-Raphson or stochastic gradient descent Bayes that can be used to do parameter estimation. And finally, you can do state estimation. So either Kalman filtering, Kalman smoothing, either using the Kalman filters formulation or the more numerically robust UD formulation. And finally, you have several post-processing tools, either to visualize the results and also to export plots. So all the plots you've seen here are directly exported from OpenBDLM. This is for you to be used. And finally, it is, and it's going to remain an open platform, so you can directly use it and also develop your own tool specifically designed to address your need if it's not already fulfilled with what's in there. So in summary, we've already seen in the previous module what is the core theory with state space model. Now what we've seen in this module, how can we build linear model structures in order to build a vast variety of model that can adapt to pretty much any time series behavior you can encounter in the context of time series analysis. Okay, and this is under the umbrella of Bayesian dynamic linear model. Okay, where we use these generic blocks, we mix and match them together in order to build our A, Q, F, and R matrices that are going to be solved into our state space model formulation.